So when it comes to centrifuge, we have talked about the principle, the uh, process of sedimentation, how sedimentation occurs, what are the factors that contribute to sedimentation process, what are the hindrances, etc. Now, how to calculate settling velocity, what is the time required, how to calculate that, what is centrifugal force, how to calculate that, all these RCF and RPM relationship, all these things we have learned in yesterday's lecture, right? Now it is something like the introductory part related to the design of the instrument. Now, when it comes to a centrifuge, as you can see, this is what you actually see as an instrument, and inside is the rotor, and the rotor holds the tubes. Yeah, right. So you are going to have a chamber. In the chamber, rotor is placed, and the rotor is going to have sockets in which your tubes will be placed. This is the control panel. Set the temperature, to set the revolutions per minute, uh, cooling time, or if you are going to have the time set for these many minutes at this speed, particular RPM you have to set, so on and so forth. Then this is the lead and cover. Of course, the gasket is here, which is going to tighten the lead properly, because when you are running an instrument at very high revolutions per minute, that is very high speed, then that time the force generated and the vibrations which are going to get generated are going to be voluminous, and so tight packaging of the lead is very important. So this is with the rubber gasket, as you see in the inner lining also is made up of rubber gasket. Then these are the latches which are going to lock the lead, and very importantly, this center part of the rotor, on which the rotor center, what we call it, the shaft on which it is anchored, is going to be very important. So this is the rotor, as you can see a section on it, and this is the drive shaft, and this is the electric motor which is going to provide the spin, provide the speed. So this shaft is very important, and this is considered as the central axis of the instrument. So when it comes to the design of the instrument, the components are rotor, motor, and the the centrifuge tubes, right, in which you are going to hold the samples. Now, out of these, much is to be discussed about the rotor assembly, because it is going to be the component which is going to decide the sedimentation efficiency. When we say rotor assembly, you are going to have a drive shaft on and a rotor which is mounted onto it. So drive shaft is going to provide support for the rotor component, and the rotor head is attached to the motor, which bears the containers to house the tubes. So your tubes will be held in that, and the motor is going to provide the energy so that the rotor moves. Right. Now, what are the types of the rotors? Is it that you have only single type of rotor? No, of course not. There are different types of rotors which are available, and that is going to have effect on sedimentation process. How? That is what we have to learn. So you are going to have fixed angle rotor, swinging bucket rotor, vertical rotor. These are the three common types of rotors that you might have seen in the laboratory. Right? When I say fixed angle rotor, the word itself tells you fixed angle. So rotor tubes are held at a particular angle, and that is also very much optimized. That is, the angle is going to be between 14 to 40 degree. So the particles have to travel a particular distance in the tube, and then it is going to move down radially outwards and then settle. That is how centrifugation works. So sedimentation is going to take place at the walls of the tubes and at an angle, since the sedimentation direction is outwards due to centrifugal force. All right. So what I'm talking about this, let's see a picture related to that. So here is a fixed angle rotor. All right. You are seeing here. So when you put it on that time, this is the initial situation, your angle of the tube, because this is like the cross section of the rotor. For example, even simpler diagram I would like to share first. It is from the book, so it is not that attractive. It is in black and white, but yes, this is the central shaft, right, which is referred to as axis of the rotation. So this is the center of that. This is one. a tube, another tube is held here in the horizontal position. So when you apply the centrifugal field, the tubes are going to get pulled away if it is a swinging rotor. But if it is a vertical rotor, tubes will remain in this particular fashion. That is, they are parallel to the shaft. And if it is a fixed angle rotor, your tubes are going to be held at a particular angle, 40 to 14 degree, in the range of that. So angle of the tube will be like that. Now let's know the terminology. When you are talking about the formula for centrifugal force, we have seen that it is going to consider omega square r, right? And of course g, that is with relevance to gravitational force. So that r, from where does it come? Now let's see that pictorial picture that tells you about the how is r generated. Now this is what is the central shaft, this is the holder of the centrifuge tube, and your centrifuge tube is placed here. Now this distance from shaft to the outer wall of the tube, that is one. Shaft to the center of the tube, that is another one. And shaft to the outer wall of the tube, that is another one. So there are three R values. So this is R minimum, R maximum, and at the center you have R average. Same applies to the swinging bucket rotor also, where the uh, rotor tube or the sample tube is at perpendicular to the central shaft. Now it is entirely horizontal, right? Now how to calculate the distance? Again, it is from the outer margin of the tube, which is closer to the shaft. So this is R minimum. The distance of the particle, you can imagine this is a tube and sample is here and the particles are distributed all over the tube. So from the center of the tube, you are going to draw a perpendicular line, and that distance is going to be r average, and outer boundary of the tube, that is r max. So r minimum, r max, and r average, these three values are very important, because you can imagine a sample and that is filled in this tube, and all the particles are distributed equally all over the tube. Now the particle which is present in this position will be experiencing different force as compared to the particle which is at the outer boundary of the tube, right? Because r is the factor which is going to contribute to the centrifugal force that is exhibited and that is experienced by the settling particle. So you have to remember the concept r minimum, r average, r maximum, right? So this is your tube originally held in a vertical position. As you start the centrifuge, it opens up, uh, or it spreads out, you can say horizontally, provided it is a swinging bucket rotor. So it, the tube swings out, right? That's why the name is. And now you can see this is the boundary, this is the position of the particles uniformly spreaded over. And as the time of centrifugation process progresses, you see settling particles and forming the zones or bands. So at the end of centrifugation, you will get particles separated into compact bands depending upon their sedimentation coefficients, right? So this diagram is to tell you about three things. One is, what are the types of rotors? So this is if the rotor is having a position of the tube which is going to remain in parallel to the shaft during centrifugation, also it is vertical rotor. If the tube opens up and gets split horizontally, right, as compared to the central axis, with reference to central axis, if the tube is at horizontal position when the rotor is on, then it becomes swinging bucket rotor. And third possibility is that your rotor is fixed and it is at a particular position. So if you imagine a rotor having fixed angle, the position of your tube will be something like this. If this black arrow is the shaft, and with reference to that, this is your tube holder. So the tube is having about 14 to 40 degree angle with reference to central shaft, right? That is how three designs you can think. You can imagine how the rotor designs are. One is vertical rotor, one is swinging bucket rotor, and third is fixed angle rotor. Why to talk about it? You can think that, I mean, maybe the question arises when you're talking about sedimentation of a particle in a uniform centrifugal field, then the particle should settle at same time, right? Because the same speed is given or same centrifugal field is applied, right? So It is not right. Fact is, the nature of the rotor that is used or the rotor design that is used is going to have effect on the efficiency of sedimentation. The effective radial dimension R value that we have seen, R minimum, R maximum, and R average. These are effective values for three different types of particles which are positioned at three different locations in a tube. And based on the design of the rotor also, these R, that is radial dimension, also is going to change. So effective radial dimension of a particle will change according to its position in the container, and the container is going to hold it at a particular position depending on what type of rotor it is, right? So when you're talking about centrifugal field that is applied, uh, which is proportional to omega square r. You remember the formula that we had discussed in the previous lecture. So a particle will experience a greater field the further away it is from the axis of rotation. If it is close, it will experience close to the shaft, it will experience less force. If it is away from the axis, it is going to experience greater field. So when you are talking about the centrifugal field which is working in case of fixed angle rotor, right? Now when I say fixed angle rotor is this type, right? This is the central shaft and this is the position. It is of the tube. So it is at a particular angle. So when you think about the centrifugal field which is there experienced by the particle in this tube which is in a fixed angle rotor, it is going to differ by factor of 2. So if you just what is factor of 2 I am talking about, that is a particle is here, and particle is here. Three different positions. So the centrifugal force experienced by particle at this end, particle in the middle, and particle at the outer boundary is going to be different. So at the top, again, top of the centrifuge tube, the angle is less, and at the bottom of the centrifuge tube, it is more away from the central shaft, right? So again, the particle here and the particle here also are going to experience different centrifugal fields or force, right? So the sedimentation rate of the particle at the bottom of the tube, if the particle is here, so it is having more R, right? So if you measure the distance, this is central shaft, right? And the distance, this distance, and against that the distance of the bottom particle in the bottom region, you are measuring say 10, and that is in the top region, see it is probably 4.2, just imagine, because it is almost double that of it. So the force that is experienced by the particle at the bottom will be almost double than the particle which is present at the top. So sedimentation rate of particle at the bottom of the tube will be double that of the particle which is similar to it, entirely identical to it, but its position is at the top of the tube, because the factor which contribute to sedimentation is not only the angular velocity but the radial distance, and radial distance is going to be different when you are talking about a fixed angle rotor. So particles are going to experience different centrifugal fields. So if you can imagine that particles are moving under a centrifugal field, and they will be moving, say they will tend to move faster when when they are at the top, or when they are reaching to the bottom. Surely when they are at the top, that time the distance from the central shaft, that is the R value, is less, right? So they are going to experience less centrifugal field. So sedimentation rate also will be less. But as the particle migrates and reaches towards the bottom, that point it will experience uh, mo- a more centrifugal field, and it will move faster. So of course, you have to have a non-viscous medium. In the viscous medium, resistance by the medium also will be there. So you can imagine a particle settling in water and a particle settling in glycerol, or particle is there in oil and it is suspended. Same centrifuge angle, same speed, but the particle in the water will settle fast as against oil and as against glycerol, because viscosity is high of oil and glycerol. So the factors which contribute to the movement of the particle, they are very well given in this diagram. You can see rho, you can see d, right? So what are these? Rho is to the density. So density of the particle and density of the suspending media, both are very important. Also, can you imagine the particle is in the liquid and it is going to move away towards the outward side of the or outer wall of the tube when the centrifugal force is applied. So the particle moves outward and then slides and then settles down. So when it hits the inner boundary of the tube, that dash will push it back into the suspension. Can it happen? Can you imagine that? The particle is moving, it has reached to the outer side of the tube, outer wall of the tube, and it from there it will start migrating down. But before that, will there be any push which is going to push the particles towards the center again? Yes, that is going to be there, which is called as wall effect. And that wall effect is going to generate a kind of negative force and sedimentation is going to get affected. So you are going to have some advanced designs which are referred to as zonal rotors. We will come to that a little later. Right now you can imagine about a fixed angle rotor and the particles are sedimenting. The particle which is at the top will sediment at a less faster rate as against the particle is at the bottom. So the particle at the top, when it reaches to the bottom, it will be sedimenting faster. So the when you talk about relative centrifugal field, that is average radius that you have to take into consideration. In the previous diagram, we have seen this point. Yes, this one, right? This is R minimum, R maximum, and R average. So you have to consider R average when you are calculating the probable centrifugal field experienced by the sedimenting particle. So average relative centrifugal field, that is RCF average, is numerical value average of values extracted of R minimum and R maximum. या दोन्हीची average जी असेल, that is going to be RCF average, as simple as the meaning of the term, that is average, minimum, maximum, and average. If the sample container is fully filled, as you see in the diagram, that is one case. Can you imagine that the sample container is partially filled, right? So, will there be any difference in the sedimentation velocities that are of the particle? Sample is same, particles are same, but you have half filled or partially filled tube. What will happen? So in case of fixed angle rotor, what you are seeing on the left side, that is labeled as A, it is fixed angle rotor, and another B, other one is B, which is showing horizontally placed tube, which is swinging bucket rotor. So very sure that the minimum radius is increased and the particles will therefore start to sediment at a higher gravitational field and have a reduced path length to travel. Can you understand this sentence? What I mean to say, if the tubes are filled, the molecule at the top, a particle at the top, not molecule, particle at the top, will be experience less force against the particle at the lower end of the tube. Similarly, inner end, outer end, R minimum, R maximum. So if R maximum is there, more centrifugal field will be experienced. That is one thing. Now second case we are imagining, that is tube is half filled. In that case, of course, in that case, and the distance that particle has to travel. What is the distance? The distance is 2. Particle is here, so it has to go outward and then settle down and come here, right? So if it is half filled, right, so total distance the particle has to move also is reduced to half. So total centrifugal field experience and the sedimentation rate and the time required to sediment all will be more efficient. That means in less time and faster settling of the particle would take place if your tube is partially filled, right? So if you want to have a quicker sedimentation, you should not fill the tube completely, right? Now when you talk about centrifuge speed for a motor or the rotor that you are using, maximum relative centrifugal field which is going to get generated is going to be ready to conversion of RCF. So RCF to revolutions per minute. That conversion if you do for R minimum, R maximum and R average. So you will get to know that the sedimentation rate or velocity of a particle can be talked in terms of sedimentation rate per unit of centrifugal field, and that is what is the S value. Alright, yesterday's lecture we have seen that formula. Now here are the different types of centrifuges. Based on type of rotor, you have fixed angle rotor, you have swinging bucket rotor, and you have vertical rotor. The three designs we have seen, right? Now, if you want, I can reshare the diagrams, more simpler diagrams, right? Now, this is for fixed angle rotor, right? What do you have? This is a central shaft. You can imagine this is tube held, and so the particles are moving outward. They are sliding down the wall and settling. Against that, when you're talking about swinging bucket rotor, that time the arrangement of the tube, the sample holder is exactly perpendicular to the central shaft. So this is how you can represent the uh, types of rotors by showing in the position of the tube held or the sample holder which is held in the rotor. Now that is another thing. I'll be coming to these diagrams later on, but yes, this is another diagram. Here you can see the centrifuge is going consist of series of inverted cones. All right, they are stacked one above the other. This is one cone, then second cone, third cone, like that. So and there is minimum spacing between them. So as the feed stream moves upwards, right? Solid stream, feed stream, you are seeing these titles, right? So this is the feed stream, it moves upwards. Um, the rotation of the disk causes solid particles to move along the radial direction towards the walls. So the particles will be moving outwards, and these are the solid particles, they will be settling, right? So the particles will be moving outward and then they will be settling, similar to your other types of rotors. However, the design of the rotor cabins, or you can say the centrifuge compartment, is different here. So this is this type of a centrifuge. So you have different designs. So fixed angle rotor, swinging bucket rotor, vertical rotor, zonal rotor, and this type of centrifuge rotor, right? So these are the different designs. Let's go back to the discussion. When we talk about types of designs of centrifuges, most important are the types based on rotors, the five types: fixed angle rotor, and the centrifuge with fixed angle rotor, centrifuge with horizontal rotor, swinging bucket rotor, vertical rotor, disc type rotor, and zonal rotor. Another type is preparative rotor, preparative centrifugation and analytical centrifugation. And third type is based on speed: low speed, high speed, ultra high speed. That is how we categorize centrifugation centrifugation types. So when I say the preparative centrifuge, that means you are going to separate out a specific component from the sample given. Maybe you have a fermentation broth, the cells are there, you want to separate out the cells who have carried out the fermentation, and broth you want to separate to extract the product. So that can be referred to as preparative centrifuge, for example, right? But preparative centrifuge, when you are talking, it also can be of different types. First is differential centrifugation. Second is density gradient centrifugation. Third is red zonal centrifugation. That is how you have different types of preparative centrifugations. So when I talk about differential centrifugation, what it does, it separates particles based on shape, size, and density. A suspension of particle with varying densities or sizes, they will be sedimenting at different rates, different speeds. So larger and denser particles will sediment first, more quickly, right? And the smaller particles, or the particles with lesser density, they will be moving uh, slowly to the bottom, and they'll be settling uh, later than the heavier particles. So you are going to have a series of centrifugation cycles. So if it is to separate the suspension of cells, or you are going to have uh, um, cell lysate, and then you want to separate out mitochondria from the cells and ribosome from the cell, and then different types of components in the cell, you have to go for differential centrifugation, right? Now we will talk about differential centrifugation in details. Just give me a moment to share the another slide with you. Let me check. Right. So here I'm sharing the screen where differential centrifugation would be little more clear to you, right? So here I have taken the cell light set, right? And I want to separate out particular component, say microsomal component, microsomal fraction of the cells. Then I'll have to go for repeated or multiple centrifugation steps. And every time I have to remove the supernatant and I have to remove the pellet. So see here, here is the homogeneate. I am centrifuging it at 500 G for 10 minutes. The tube you see is with the pellet, and there is a clear supernatant. You don't see anything here. That pellet is removed, which is the nuclear fraction. I'm talking about, say, a eukaryotic cell, right? Then I have to take this supernatant, proceed for another set of centrifugation, which is run at 10,000 G, and the time is of 20 minutes. This time I will get the pellet, which is going to be composed of mitochondrial fractions, and the supernatant is removed and it is again run for centrifugation. This time the speed at which I am running is 1 lakh G, and it is run for 1 hour. So I'll get cytoplasmic proteins in the supernatant, and in the pellet I'll get the microsomal fraction. That is how I have to set the centrifugation time and speed depending upon the density, mass and size of the fraction that you want to separate using differential centrifugation, right? So differential centrifugation is used for separating the components of the cell. Now, further, this technique of differential centrifugation is complemented with affinity principle also, right? So, for example, if you want to separate glycoproteins from the cell, can you take help of centrifuge? Is a question to you. We will talk about it in the next lecture. But yes, in today's overview, at least you get to know that you are going to use differential centrifugation for fractionating the cell components and extracting or pelleting the desired fraction of the homogenate. Second is density gradient centrifugation, in which you are going to separate particles based on their ion density or sedimentation rate. So when you have a mixture of a sample homogeneate that you are going to load on the density gradient column that is developed in the centrifuge tube. Now, what this density gradient is made up of? It is made up of cesium chloride, or sometimes sucrose gradient also is used. So, for isolation of plasmids, nucleoproteins, viruses, DNA bandings, you can take help of cesium chloride gradient. NABR, NAI, right? So these are the salts which are used for fractionation of lipoproteins. Percol, ficol, dextran, they are used for separation of whole cells based on the density. So for example, you are taking a tissue sample which is infected with bacteria and viruses, and you want to separate viruses, you want to separate bacteria, and you want to set the whole cells. How will you go for it, right? So maybe first would be doing with filtration. So bigger size cells will be remaining in the on the filter, and bacteria and viruses will move down. But yes, centrifugation using picol or percol or dextran type of gradient, you can separate out the whole cells. And of course, when it comes to separation of enzymes, etc., also sucrose gradient is used. So these are different types of gradients which are used for separation using density gradient. How it works, we know, right? Density gradient centrifugation, when we talk about, I'm sorry, a schematic diagram I have to show, but yes, it is going to be based on the density of the particle, and that matches with the density of the gradient, and you are going to get such zones form based on matching of the density. So denser the particle, it will be forming a band at the towards the base of the tube, and lighter the particle, it will be forming the zone, or will get concentrated at the top of the tube. So because the gradient is of the nature that you have lowest concentration at the top and highest at the bottom. So when the particle matches its density, when the density of the particle matches with that of the gradient at a particular zone, it will form a band. So on top of density gradient, the sample is loaded or overlaid, and then depending on mass particle, the the particles will travel down the tube, and it will travel down at different speeds, different forces they will experience depending upon their mass, their position, and they will move towards the outer wall and then will slide down, and but will form the zone which is going to be called as a band, where the density of the medium and density of the particle, they match, they are comparable, and you are going to get separate zones formed. That is how you can schematically show this. All right, so this is how you can take a overview of centrifugation processes or methods. So differential centrifugation, red zonal, all right, then isopycnic density gradient. That is how different types under preparative centrifugation we are talking. So uh, individually differential centrifugation can be asked as a separate question for 7 to 8 marks. Density gradient can be asked for 7 to 8 marks, or a question for 15 marks that would be like give overview of centrifugation processes. Under that you need to write a summary of all these, and such a short summary with the diagram will be enough to complete the answer, right? So today we talked about different types of rotors, right, and overview of preparative centrifugation processes, right? So with this, the initial discussion about overview on on centrifugation processes is done. Now each of these we have to learn in detail, because mm, that can be that needs to be studied for more details. For example, when I say preparative centrifuge, as if I have to separate ribosomes, if I have to set microsomal component or mitochondria, then surely it has to be a ultra high centrifuge, right? That is rotating at a speed of at least 80,000 revolutions per minute. And when I say 80,000 revolutions per minute, that means 80,000 multiplied by 980, that will give you relative centrifugal field of 6 lakh G. So if such a kind of speed you are going to use, and for sedimenting the particles, a lot of heat is going to get generated. So these instruments are generally refrigerated, they are sealed, and they are evacuated also, because even a simple air current at such a high speed is going to be damaging. So such instruments are refrigerated. Preparative ultracentrifuges, I am saying, are refrigerated, they are sealed and evacuated. This is why, just to minimize any heat up or excessive rotor temperature that is going to get generated due to friction, the resistance between air and the spinning rotor that will heat up the system, and so that it is to be maintained at refrigeration temperature, so that there is no damage to your molecule, right? So temperature monitoring system also is there, and which is a very sophisticated system in ultracentrifuges. So you are going to have the specific sensors for temperature sensing. So infrared temperature sensors that are going to continuously monitor the rotor temperature and control the refrigeration system, they will be working. So overspeed control systems are there, which are also inbuilt. We are talking about the types and parts in the component. So in addition to rotor, in addition to shaft, you have the refrigeration system, which is going to monitor temperature, control refrigeration system. You are going to have over mm, overheating control. Similarly, uh, you will have a system which is going to control the operation of the rotor. so that to prevent any movement, any higher speed which is going to get generated. So under control the system has to be. So electronic circuits are there which are going to prevent operation of the rotor above its maximum rated speed. So that system is the part of it. Then vibrations are going to be there to minimize these vibrations, uh, because if there are vibrations, the rotor will be slightly imbalanced, and that is going to break the shaft at such a high speed. So you have to minimize the vibrations. So balancing of the rotor, any unequal loading of the centrifuge tubes also can cause this kind of a damage, right? So you have to have a shaft which is flexible drive shaft system. If there are hard metals, they will, or alloys, they will break at that speed. So flexible fabricated shafts are there which are going to allow the rotor imbalance due to vibrations. So these are the additional components in the system. Centrifuge tubes, of course, are one of the important components in the system. They are going to be very important. They need to be of the material which is non-erodible, non-corrosible, and they are easily washed, and they are going to be like very clean they should be, and they should be of similar weight, so that when they placed in that centrifuge, one opposite to the other, the balance of the centrifuge rotor will be maintained, right? So you are going to have different types of preparative ultracentrifuges. It could be air driven, which is called air fuse, right? So they are available.